Hi, this lesson based on Edexcel IAL Unit 6 paper. So, this Unit 6 paper mainly consists of error calculations, then questions related to experimental techniques, then graph. Okay, so students have no problem. Most students have no problem related to experimental techniques because they do practical at school and they learn the experimental techniques through their experimental practical lessons. Also, graph is not a problem. Most of students they handle it, but the main problem is related to error calculation. Okay, actually, even we call it as error calculation. It's nothing related to error. It's something related to uncertainties, percentage uncertainties, percentage differences. Okay, why are we interested about these percentage uncertainties and percentage differences? The reason is whatever the practical you do, finally, you need to give a conclusion of your practical. Say, for example, you are measuring the gravitational acceleration by using simple pendulum. There you are getting a value for gravitational acceleration, say g is equal to 9.56 meter per second squared. But we know the actual value of gravitational acceleration is 9.81 meter per second squared, right? So are you going to say at the end of your experiment, are you going to say my experimental value, which is 9.56, is not equal to 9.81, so I am not accepting the practical? Or are you going to say that my experimental value is a little bit closer to the actual value, which is 9.81, so I am accepting it? No, neither way is right? So you can't say any conclusion like that. You need to have a scientific method to give your final conclusion whether the experimental value, what you got through the experiment, is acceptable or not. To do that final conclusion, we need a mathematical approach called error calculation. It's nothing related to error. Even if you do very carefully without making any mistake, you might not get the actual value of 9.81 because that depends on the uncertainties of the experimental instruments you are using in the laboratory. Due to the uncertainties in the measurements you make, there's nothing wrong, there's no mistake, no error, but uncertainties of the measuring instrument, due to that your final experimental value might deviate from the actual value. So in that case, we need to have a method or approach to give the conclusion. So that's the reason we learn about this error calculation, but actually not an error. Okay, so I thought of discussing a few examples and little bit of revision, quick revision and theory related to error calculation. Then I'll discuss the past papers, few recent past papers, right? Because I thought of doing this error calculation revision before starting papers, then it will be easier for me to do the papers without any difficulties. Okay, first you should know the word precision or least count of a measuring instrument. What do you mean by least count or precision of a measuring instrument? Means the minimum value an instrument can record or minimum reading an instrument can record. That value you must remember for certain instruments like meter rule, 1 millimeter. It can't measure anything smaller than 1 millimeter. Vernier caliber, normal analog vernier caliber, that is 0.1 millimeter. Micrometer screw gauge, 0.01 millimeter. Normal ordinary protractor, 1 degree. Most of the laboratory thermometers, liquid in glass thermometers, mercury thermometers, there are two different types we have at school that normally it could be either 1 degree Celsius least count or 0.5 degrees Celsius. So you need to know these values better to remember the least count of these instruments. Okay, next thing is uncertainty. Uncertainty means, normally I don't want to go in detail that you would have learned, but I'm dealing about the calculation part. So how do we take uncertainty? Normally we take uncertainty of single measurement by an instrument is taken as half of the precision of the instrument. Say for example, when you are taking measurement by using a meter rule, the uncertainty in the measurement of the length is 0.5 millimeter. If you are taking measurement by using a protractor, the uncertainty in the measurement of that angle is 0.5 degree. If you take a measurement by using a vernier caliber, the uncertainty will be half of 0.1 millimeter, which is 0.05 millimeter. So we know the precision of micrometer screw gauge is 0.01 millimeter. So the uncertainty will be 0.005 millimeter for the single measurement recorded by a micrometer screw gauge. Okay, so based on that, we can calculate for a single measurement, we can calculate the percentage uncertainty. So percentage uncertainty, shortly we write percentage uncertainty of a single measurement is equal to uncertainty over measurement into 100%. Normally, in Edexcel, percentage uncertainty is given in two significant figures. So remember that there's no reason, but they normally accept or give in the maximum also the percentage uncertainty of a single measurement, or normally percentage uncertainty is given in two significant figures. Okay, so based on this, I'm going to do a simple question now. Okay, so first simple question I wrote it. Thickness of 10 sheets is measured by using a vernier caliber. You know the precision of vernier caliber is 0.1 millimeter. So the uncertainty in the measurement will be 0.05 millimeter. Okay, so the total thickness of 10 sheets is recorded as 7.8 millimeter. Find the percentage uncertainty in the measurement. So you are measuring the thickness of 10 sheets. So what's the percentage uncertainty in the measurement of 10 sheets is, you know, the equation percentage uncertainty equal to uncertainty of the measurement. So uncertainty in the measurement is half of the precision. So you are using vernier caliber, which has precision 0.1. So half of it, 0.05 millimeter, 0.05 millimeter over measurement. Measurement is 7.8 millimeter into 100%. So the percentage uncertainty in the measurement will be equal to 0.64 percentage. That's the first part answer. Second part, find the thickness of one sheet. So you know the thickness of 10 sheets, that is 7.8. So thickness of one sheet I'll denote by T. So that will be 7.8 millimeter divided by 10. So that will be 0.78 millimeter. Third part, state the percentage uncertainty in the thickness of one sheet. Careful. So that remember that whenever a measurement is divided by a number, the percentage uncertainty will remain the same. Okay, again I'm telling it. Whenever a measurement is divided by a number, so here the measurement is 7.8 millimeter. It is divided by 10 to get the thickness of one sheet. We found the percentage uncertainty of the measurement, that is 0.64 percentage. So when we divide the measurement by 10, the percentage uncertainty will remain the same. It never changes. Remember that whenever a measurement is divided by a number, or even when you multiply by a number, I'll give an example. Next example is based on that multiplication. So whenever a measurement is divided by a number or multiplied by a number, the percentage uncertainty will not change. It will remain the same. So here you are dividing it by 10 to get the thickness of one sheet, but the percentage uncertainty in the measurement of thickness of one sheet is also 0.64 percentage. So third part, the percentage, that's what they say state. State the percentage uncertainty in the thickness of one sheet, that also 0.64 percentage. Okay, so fourth part, find the uncertainty in the thickness of one sheet. So that also I'll do a calculation. After doing the calculation, I'll give you a conclusion, important conclusion. So I can see the uncertainty in the thickness of one sheet in T. T means thickness of one sheet. So uncertainty in thickness of one sheet is equal to thickness, that is, we can say the thickness of one sheet is 0.78 millimeter into the percentage uncertainty is 0.64 over 100. Solve it. You will get 0.78 005, you will get it. Okay, so carefully note that the uncertainty in the thickness of one sheet, symbol T stands for thickness of one sheet. I'm using that notation in this question. So uncertainty in the thickness of one sheet is 0.005. If you compare this value with this value, you will come to know that uncertainty is divided by 10. Is it 0.005 is equal to 0.05 divided by 10? So remember that. Another conclusion, whenever a measurement is divided by a number, uncertainty also will be divided by the same number. Say uncertainty of the measurement is 0.05. So we are dividing the measurement by 10. So if I divide the uncertainty of the measurement by 10, I will get this answer. But the percentage uncertainty will remain unchanged. This is true whenever you are dividing a measurement by a number, or when you are multiplying a measurement by a number, percentage uncertainty will remain unchanged, but uncertainty will be divided by the number when you are dividing it. Uncertainty will be multiplied by the number when you are multiplying it. So remember that. Okay, so that is 0.005 millimeter. Fifth part, find the range of the thickness of one sheet. So I can say the range of the thickness of one sheet. I can say, I know the thickness of one sheet is 0.78 millimeter plus or minus 0.005 millimeter. So this minus this, that will be 0.775. 3SF I can give no problem. 775 to 0.785 millimeter. So what do you understand by this range? What's the meaning of this range means? By using the instrument given to me, the instrument given to me is vernier caliper. By using that instrument, when I measure the thickness of one sheet, finally I can say, I am not sure what is the thickness, but I know the thickness is somewhere between these two values. But I am not sure about the actual thickness of it. But I can say the thickness of one sheet is somewhere between this and this. That's the meaning of this uncertainty, and that's the actual value we need to, or that's a final conclusion we need to accept in this simple measurement of the experiment related to a measurement. Okay, so this is the second question. Diameter of a coin is measured by using a vernier caliper and recorded as 12.6 millimeter. Find the percentage uncertainty in the measurement. First part. Okay, find the percentage uncertainty in the measurement. So percentage uncertainty is given by uncertainty in the measurement divided by the value of the measurement. So the first part answer, I can say percentage uncertainty in the measurement is equal to, we are using a vernier caliper. So the uncertainty in the measurement of vernier caliper by using a vernier caliper will be 0.05. So that is 0.05 millimeter divided by the measurement, that is 12.6 into 100%. So that will be equal to 0.40 percentage. Second part, find the circumference of the coin. You know, circumference is given by pi d or 2 pi r. So 2 into r is diameter. So pi d, I can say pi into d. So you are multiplying the measurement, which is d, by using pi. So that you can say pi into d. If you substitute the value of d, which is 12.6, so pi into 12.6 millimeter, you will get, that will be 39.6. Normally we give in 3SF, mark scheme accepts in 3SF, so 39.6 millimeter. That's the circumference. Third part, state the percentage uncertainty in C. So I told you, whenever a measurement is multiplied by a number or divided by a number, percentage uncertainty will remain the same. So here measurement is 12.6 millimeter. It is multiplied by a number. Pi is a number, you know that, 3.14 something, you can get it in the calculator. So when you multiply the measurement by a number, the percentage uncertainty will remain the same. So the percentage uncertainty for third part in the circumference also 0.40 percentage. Okay, so fourth part, find the uncertain range. So here actually, I don't need to calculate it. I can simply say, I told that already. When you multiply a measurement by a number, uncertainty also will be multiplied, but percentage uncertainty will remain the same. So uncertainty in the measurement is 0.05. If I multiply 0.05 by pi, I will get the uncertainty in the circumference, but I'll do the calculation and show you, you will get the same answer. So I do the calculation. Uncertainty C is equal to the value of the circumference, 39.6 millimeter, into the percentage uncertainty 0.40 over 100. You will get a value that is equal to 0.16 millimeter. So that's the uncertainty C. But if you multiply this way, try, you will get the same answer. The same thing, rather than doing this way, if you say this way also, you will get the same answer. That is pi into uncertainty 0.05. You will get the same answer, 0.16 millimeter. So remember that whenever a measurement is multiplied or divided by a number, uncertainty also will be multiplied or divided by the same number. Remember that. Okay, next we are going to learn how to find the uncertainties, percentage uncertainties for certain physical quantities. Those physical quantities are not directly measured. They are calculated through some other measurements. Okay, so in such situations, how to find the uncertainty and percentage uncertainty. I already told the purpose. Why do we learn, or why do we need uncertainty, percentage uncertainty? Because to give a final conclusion. So if you can't give final conclusion regarding your experiment, there's no point of doing experiment, is it? So finally, we need to give a conclusion whether my experimental value is acceptable or not, or up to what extent it is acceptable. To know that, we need to do error calculation. We call this uncertainties, percentage uncertainties. Okay, so I already told that earlier also. So again, I remind you that one. So how to find the uncertainty, percentage uncertainty for certain physical quantities where we don't measure them directly. We find out, or we calculate by using some other measurements. Say for example, we don't normally measure the change in temperature, is it? We don't measure the change in temperature. We normally measure the initial temperature, then final temperature, then subtract the initial temperature from the final temperature to calculate the increase in temperature, or to calculate the decrease in temperature. We subtract the other way. We subtract the final temperature from the initial temperature if it is temperature is going down, decreasing. So there we don't measure the change in temperature, is not measured. We measure the initial temperature and final temperature. That means there we are measuring two different quantities, that is initial temperature, final temperature, and we are subtracting one from the other. Same way, certain situations we don't measure directly. Say for example, if you are measuring the perimeter, we measure all the four sides and add them. There is no measurement, no way of measuring the perimeter directly. We measure the four sides of, if it is a rectangular shape wooden block, we measure the four sides because maybe they are not same, and we add them. Okay, so next I'm going to explain how to find the uncertainty and percentage uncertainty when measured quantities are added or subtracted with each other. Say for example, let x and y are the measured quantities. So x and y are can be like initial temperature, final temperature, or x and y could be one side of a like something like a length or whatever it is. X and y are the measured quantities, and z is the physical quantity calculated by using x and y. So I can say the physical quantity which is calculated is z by using x plus y, or z is calculated by using x minus y, where x and y are the measured quantities and z is the calculated quantity. Okay, so here these are the measured quantities. All measured quantities have uncertainty because we are using an instrument to measure those quantities. All the measuring instruments have uncertainty. You know that half of their precision. So X and Y has uncertainties. So how to calculate the uncertainty of Z? Okay, remember that. Whether the measurements are added or subtracted, uncertainty in Z is equal to uncertainty in X plus uncertainty in Y. Whether they are subtracted or added, whatever it is, uncertainties will be added. Then how do you find the percentage uncertainty? Percentage uncertainty in Z is equal to uncertainty in Z over value of Z, that is what you got here should come here. Sorry, what you got here, this value should come here, value of Z into 100%. That's the way we calculate whenever two measurements are added or subtracted. Okay, based on this, I'll do a simple calculation next. Okay, so this is a simple question. Initial temperature given 32 degrees Celsius, final temperature given 85 degrees Celsius. Find the increase in temperature. So that's simple. You can say increase in temperature. We do that in specific capacity MC delta T. Yeah, you know that. So increase in temperature delta T will be equal to final temperature 85 minus initial temperature 32. That will be equal to uh, that will be equal to 53 degree Celsius. Okay, so the second part they ask you to find the percentage, the second part is find the uncertainty in delta T. Okay, so here the uncertainty could be given as plus or minus 1 degree Celsius, plus or minus 1 degree Celsius. Sorry, I didn't put that earlier. So they are using a liquid in glass thermometer. So the measurement is done by liquid in glass mercury thermometer. Uncertainty is 1 degree Celsius. Okay, so the second part, how to find the uncertainty in delta T will be equal to 1 plus 1, that is equal to 2 degrees Celsius. So that is the uncertainty, because uncertainty of this one is 1, this is 1. So we need to add whether you are adding or subtracting the measurements. So third part, percentage uncertainty. Percentage uncertainty in delta T is equal to uncertainty in delta T 2 degrees Celsius divided by measurement 53 into 100%. So solve it. You will get the answer for this one. That is the percent. That will be equal to 3.8 percentage. Okay, so there are more examples. Certain physical quantities cannot be measured directly. I already explained if two measurements are added or subtracted. I gave an example where we add, where we subtract. Okay, sometimes we multiply the measurements or we divide the measurements to calculate some other physical quantities. For example, to measure the density, we don't measure the density. Say, for example, you are given a metal block, a cuboid, and your teacher is asking you to measure the density of it. So you measure the volume, you measure the mass, then you divide the mass by the volume. So the measurements are volume and mass, but density is calculated by using an equation where mass or volume, you are dividing the two measurements. Same way, sometimes we multiply two measurements. Say, for example, if you want to measure the area of a rectangle, we measure the length, we measure the width, and we multiply the length by the width. Is it? So like that, imagine X and Y are the two measured quantities, and the physical quantity Z is calculated by using X over Y or by using X into Y. We are multiplying the measurements or we are dividing the measurements to find a physical quantity Z. So in this approach, how do we find the uncertainty and percentage uncertainty of Z? Here we first find the percentage uncertainty. So percentage uncertainty of Z or in Z is equal to percentage uncertainty in X We know X is measured by using an instrument. So that measurement has uncertainty. So percentage uncertainty in X plus percentage uncertainty in Y. Okay, whether we are dividing or multiplying, percentage uncertainties will be added. Then uncertainty I need to find. Uncertainty in Z, how do we find? Uncertainty in Z is equal to value of Z, so Z into this value or this value into percentage uncertainty in Z divided by 100. Okay, so there's a simple question given again. Mass, something is measured, maybe a metal piece or something. Mass is 96.2 gram. The uncertainty in the measurement of mass is 0.5 gram plus or minus. Volume is measured for the same object, 14.8 cm cube. The uncertainty is 0.2 centimeter cube is the volume. First part, find the density rho. So we can give it in gram per cm cube. Second part, find the uncertainty in density. Okay, so first I need to find the density. Density is given by mass over volume, you know that. So the answer first part, you know that density equal to mass over volume. So mass is given as 96.2 gram. Volume is given as 14.8 cm cube. So solve it. You can give it in 3SF. So when you solve, the density will be 6.50 gram per cm cube. That is the density. Right, second part, I need to find the uncertainty in the density, but I can't find the uncertainty directly. First, I need to find the percentage uncertainty because the quantities are divided by each other. So I need to find the percentage uncertainty. So how to find the percentage uncertainty? Second part, percentage uncertainty in density will be equal to, we are dividing, that will be equal to percentage uncertainty in mass plus percentage uncertainty in volume. Percentage uncertainty in mass, what will it be? Uncertainty in mass is 0.5 grams. So 0.5 gram divided by the measurement 96.2 into 100 plus percentage uncertainty in volume is uncertainty in volume 0.2 divided by 14.8 into 100. So the percentage uncertainty will be finally 1.9%. We normally give it in 2SF, 1.9%. Now I need to find the uncertainty. So uncertainty in rho will be equal to the value of the rho 6.50 gram per cm cube into 1.9 over 100. So that will be 0.12. Give it in the same decimal point, 0.12 gram per cm cube. So I can say the density rho is equal to 6.50 gram per cm cube plus or minus 0.12 gram per cm cube. So I can say, according to the given instruments, I am not sure about the density, but I can say the density of this particular material is falling within this range. Okay, so there's another method to find the second part where we find the maximum value of density, minimum value of density, most maximum, then most minimum, then half times maximum minus minimum. That also gives the same uncertainty. Okay, so I can say method 2 for the second part. So rho max I need to find maximum density. So to find the maximum density, I should consider the maximum mass and minimum volume. Maximum mass means mass plus 0.5. So I should find maximum mass, maximum over volume minimum. So how can I find the maximum? That is 96.2 plus 0.5 over minimum value of volume 14.8 minus 0.2. Okay, solve it. You will get the maximum density. So the maximum density will be 6.62 gram per cm cube. Then we find the minimum value. So where minimum mass over maximum volume. Okay, so minimum mass, how to find the minimum mass? 96.2 minus 0.5 divided by maximum volume 14.8 plus the uncertainty 0.2. So the minimum density will be 6.38 gram per cm cube. Okay, so now find, the decimals are a little not clear in the camera. So now find the uncertainty in rho is equal to half into rho max minus rho minimum. So half into maximum density is 6.62 minus 6.38. Solve it. You will get the same answer what we got earlier. That will be 0.12 gram per cm cube. We got the same answer in the first method also. Here also you'll get the same answer. This method we can use anywhere. For any type of situation, we can find the uncertainty by using this maximum minimum method. I'll do some examples later also when I discuss the past paper questions. Okay, so next thing is about a measured quantity is used to find some other physical quantity, but there will be an index. Say, for example, uh, if you want to measure the volume of a sphere, we first measure the diameter of the sphere by using a vernier caliper or micrometer screw gauge. We can find the diameter. Then we use 4 by 3 pi r cube or 4 by 3 pi d by 2 all in cube. So there will be cube, the power index 3 for the diameter. So how to calculate the uncertainty and percentage uncertainty when there is an index in the measured quantity? So for example, I can say x is the measured quantity and k is a number, something like 4 by 3 pi. So if I say z, I'm going to calculate where k is a number, x to the power n. X is the measured quantity, something like diameter or something like that. X is the measured quantity, n is an index, k is just a number. How to find the uncertainty or percentage uncertainty of z? So percentage uncertainty in z is given by n times percentage uncertainty in x. Careful, when I find percentage uncertainty, there won't be k won't be here, right? So percentage uncertainty z is equal to n times, the index come from n times percentage uncertainty in x. Then uncertainty in z is equal to the value of z, which is obtained from this equation, z into percentage uncertainty in z divided by 100. Okay, so this is a simple question again. Diameter of a sphere is measured by using micrometer screw gauge and recorded as d equal 1.83 millimeters. So micrometer screw gauge means it's a uncertainty, we know 0.005. We know the precision or the least count of micrometer screw gauge 0.01 millimeter. Half of it will be the uncertainty. Right, so first part, find its volume. So we can find the volume, first part. You know volume equal to 4 by 3 pi r cube or d by 2 cube. So that will be 4 by 3 pi. The diameter is given is 1.83. So we'll give it in millimeter cube, divide by 2 in all the cube. So that will be, we can give it in 3SF, 3.21 millimeter cube. Okay, second part, find the uncertainty in its measurement. So here the quantity has, the equation has index to the power 3. So we can't find the uncertainty directly in this method. That's the next method we can find it by using maximum minimum method. But in this method, first we need to find the percentage uncertainty. So second part I can say First method, I'm using the normal way we find the percentage uncertainty, then we'll find the uncertainty. So percentage uncertainty in volume is equal to, 4 by 3 pi r cube. The index comes from, so 3 into percentage uncertainty in D. So 3 into percentage uncertainty in 3 in diameter. So percentage uncertainty in diameter means uncertainty in diameter divided by the measurement. Uncertainty in diameter, we used a micrometer screw gauge, so 0.005 millimeter divided by the measurement is equal to, we know that 1.83 into 100%. Solve it, you will get the percentage uncertainty, that will be 0.82 percentage. Now uncertainty in volume is equal to the value of the volume 3.21 times percentage uncertainty over 100. So there you will get the uncertainty will be equal to 0.03 millimeter cube. So I can say the volume is equal to 3.21 millimeter cube plus or minus 0.03 millimeter cube. So that's the volume including the uncertainty. Okay, so uncertain volume we can do by using what I said earlier, maximum volume, minimum volume, then half maximum volume minus minimum. That method also will work. That method will work anywhere. So I'll do that method here as a second method. So method 2 for the second part. So V max I need to go. We know the general equation V equal to 4 by 3 pi d by 2 cube. So I need to find V max, maximum volume. To get the maximum value, I should get the maximum diameter. How can I get the maximum diameter? That is D plus uncertainties. So 4 by 3 pi. So the diameter is 1.83 plus the uncertainties of the diameter measurement by it's done by using micrometer screw gauge. So 0.005 divided by 2 all in cube. So that will be equal to 3.24 millimeter cube. Then V minimum, that is equal to 4 by 3 pi D minimum, that is 1.83 minus 0.005 divided by 2 all the cube. That you will get it 3.18 millimeter cube. So uncertainty in volume is equal to half into V max minus V min. That is half into V max is 3.24 minus minimum 3.18. That will be the same answer. You will get it as earlier, 0.03 millimeter cube. So here also I can say the volume is equal to finally 3.21 millimeter cube plus or minus 0.03 millimeter cube. So this method, maximum minus minimum, half into maximum minus minimum, you can use anywhere, any function it will work, either logarithmic or sine function or exponential function, anywhere you can do this method. For example, refractive index mu is equal to sine I over sine R. The uncertainty in I is I call delta I. Uncertainty in R is delta R. If I say how to find the uncertainty in refractive index, I can see to find the uncertainty in refractive index mu. First, I should find the mu max. Mu max is equal to sine I plus delta I. I need to find the numerator, the larger value, and the denominator, the smallest value, R minus delta R. Then find the mu minimum, sine I minus delta I over sine r plus delta r. I'll get the minimum value by making the numerator minimum, denominator maximum. Then uncertainty in mu is equal to half mu max minus mu min. This will work. Anywhere this method will work. Even May 2021 error calculation based on this one. When I discuss, I'll show that. Okay, so you know that there are two different types of error: systematic error, random error. Systematic error is due to default in the measuring instrument, something like zero error. Zero error means when the vernier caliper, the jaws are touching each other, zero of the main scale and the zero of the vernier scale should align with each other. Otherwise, there is zero error. Same way for the micrometer screw gauge also. So normally before we start using any instruments, even for analog meters, voltmeter, analog meter, the pointer should be at zero. If it is not at zero, all the readings will have error due to the initial position of the pointer or initial position of the main scale and vernier scale in vernier caliper. So those are called zero error. So zero error will be added or subtracted in all measurements. So the all data, all the measurements will have error. That is called systematic error. So to overcome the systematic error, we should do error correction. We have to subtract or add the initial position or initial reading of the instrument. Normally, the error calculation is not in the Edexcel syllabus, so I don't want to go in detail about error calculation, how to do error calculation for vernier caliper, micrometer screw gauges. So just we omit it, but we know there's an error called zero error, which is systematic error. So to eliminate the systematic error, we should do error correction. Uh, at the same way, if you are using a instrument and you are not familiar with that instrument, you might use in a wrong way. That also can cause systematic error. So there you have to learn how to use the instrument. Okay, these are related to systematic errors. Random error. So random error means, you know, when you are measuring the diameter of a wire by using a proper micrometer screw gauge, but the diameter won't be the same at all positions. So to overcome there, we can reduce that is called the error due to such problem, the diameter of the wire not exactly the same. So depending on the position where you are measuring the diameter, it could be slightly different. So what we do, we measure the diameter at different positions at different orientations. We should keep it like this, then rotate it through 90 degree and measure it again. So like that, 5 different places, measure the diameter and find the average when you are measuring the diameter, or even when you are measuring the time taken, repeat it and measure the average. So this repeated measurements is used to reduce the random error. Okay, you can't eliminate the random error. You can reduce the random error. Systematic error could be eliminated. I already told how to eliminate it. So random error we can reduce by using repeated measurements. So when we have repeated measurements for the same particular quantity, for the same particular measurement, you are doing the repeated measurements. How to find the uncertainty and percentage uncertainty? Say, for example, you are measuring the diameter of a wire by using a micrometer screw gauge. Imagine that micrometer screw gauge has no systematic error, but the diameter is recorded 5 times like this. First measurement, say maybe 0.84 millimeter. Second one is 0.80 millimeter. Third reading is 0.86 millimeter. Fourth reading is 0.82 millimeter. So how to find the uncertainty, percent uncertainty? Normally after having these repeated measurements, we find the mean value, you know, add everything, divide by the number of readings. Here only 4 readings are given. So add everything, divide by 4, you will get the mean diameter. How to find the uncertainty? Uncertainty in D is given by half into maximum. Among them, what is the maximum? 0.86 minus minimum 0.82. The answer should be given with the same decimal point. So here it's in 2 decimal point or 2SF. If the answer with the same decimal point, that is the uncertainty value. So here the uncertainty will be equal to 0.02. Yeah. So percentage uncertainty, how to find it? Uncertainty 0.02 millimeter over the mean value. You need to find the mean value here. That will be, mean value will be 0.83. So 0.83 into 100%. Normally you can do it in 2SF. That's the way we find the uncertainty and percentage uncertainty. But if there's a very anomaly, say something like 0.43, something like that, maybe student would have made a mistake. So if they give a value which is much differing from all other values, that we call anomaly, we don't consider that in our calculation. You have to ignore that value. So these are the error calculations related to uncertainty and percentage uncertainty. Okay, next thing is percentage difference. Okay, percentage difference means for the quantity, physical quantity you are measuring, you might know the actual value or you might know the theoretical value. Say, for example, the actual value means, the actual means it's a well-known value. Several times the exam has already done and they know the value. For example, gravitational acceleration 9.81. So percentage difference, you are getting a value of maybe 9.62. The value, your experimental value is 9.62 meter per second squared. So what's the percentage difference between your experimental value and the actual value? Means percentage difference is given by difference over 9.81 minus 9.62 divided by the actual value or the well-known value or the theoretical value 9.81 into 100%. That also given in normally two significant figures, right? So that's the way we find the percentage difference if we know the actual value or theoretical value. Okay, sometimes you might have two different values for your experiment, but you don't know the actual value. How to find the percentage difference between those two values? Say, for example, you are measuring the density of something by different methods. You have two different values, rho 1 and rho 2 for the densities, but you don't know the actual value of that particular material, the density of that particular material. How to find the percentage difference between these two values? So their percentage difference equal difference over larger minus smaller. Uh, Subtract the smaller value from the larger value over, we don't know the actual value, so we put the average value, the mean value into 100. Okay, so that's the way we find the percentage difference between two different measured quantities. Okay, so that's all related to error calculation. What we say error calculation, uncertainties, percentage uncertainty, and percentage difference. Now, next thing is about how to give the conclusion. I told that way before starting this. The purpose of all these error calculations, what we call uncertainty or percentage uncertainty, to give the final conclusion of our experiment. If we can't give, no point of learning this one. Okay, how to decide up to what extent our experimental results are acceptable. Every year there will be a question. They ask up to what extent this experimental value is acceptable, something like that. There will be question in the Unit 6 paper at Excel. Okay, to do that, I will discuss two or three past paper questions. That will be easier to explain rather than my question. So I'm going to start discussing those past paper questions to make you to understand how to give the final, how to take the final decision up to what extent our experimental value is acceptable. So based on the past papers, I'm going to explain that. Okay, first I'll discuss this question, November, that says Monday, 11th November 2019. WPH 06, not 16, it's old syllabus, WPH 0601. The first question in this paper, a student determined the density of a metal. She measured a thin square sheet of a metal. The length of each side of the sheet was 30 plus or minus 0.1 centimeter. So the length of the sheet, the each side, the length is this also same, this also same. The L is equal to 30 centimeter plus or minus 0.1 centimeter. It's given in the paper. So the answer is 0.1 centimeter. How they measure, they didn't say that. Okay, so 30.0 they are saying 30.0 plus or minus 0.1 centimeter. Okay, so she folded the metal sheet in half. She continued to fold the metal sheet in half until it had been folded 5 times. So when it is folded 5 times, how many layers will be there? 32 layers, 2 to the power 5, 2, 4, 8, 16, 32. So there will be 32 layers will be there. She used a micrometer to measure the total thickness of the folded sheet. A part, first part. State one reason for measuring the thickness of the folded sheet rather than an unfolded sheet. So the answer, now if you measure just one layer of sheet, the thickness will be much smaller. So there, what will happen? The percentage uncertainty will become smaller. You know, percentage uncertainty equal uncertainty. You are using a micrometer screw gauge, so 0.005 over. Measurement will be smaller. So the percentage uncertainty will become larger. So if the percentage uncertainty will become larger, that is not good for an experiment. So to reduce the percentage uncertainty, you are increasing the measurement. How do you increase the measurement? You are increasing the number of sheets. That is, you are increasing the number of layers by 32 times. So there the percentage uncertainty will become smaller. So now the advantage is this one. You are reducing the percentage uncertainty of the measurement, then that will be the percentage uncertainty of thickness of one sheet also. When you divide the total thickness, the measurement by 32, you will get the thickness of one sheet. So the percentage uncertainty of that also will be much smaller. You see, I told that whenever a measurement is divided or multiplied by a number, there is no change in percentage uncertainty. So you are reducing the percentage uncertainty of the measurement by increasing the number of layers, then that smaller percentage uncertainty will be the percentage uncertainty for thickness of one layer also. So what will happen? The uncertainty also will become smaller. So that is the advantage of this method, folding the paper. So anyway, just one more question. Maxim says percentage uncertainty of the measurement will become smaller. Or if you say this way also, they should accept it. But Maxim is saying percentage uncertainty will be smaller. Don't say uncertainty will be small, but if you say uncertainty of thickness of one layer or uncertainty of thickness of one sheet will become smaller, they will accept it. They should accept it. Okay, so you can say percentage uncertainty will become smaller, or uncertainty in the thickness of one sheet, that word must be there, thickness of one sheet will become smaller. So that's the answer for the A part, first part, this paper. Okay, A part, second part, explain one other technique she should use to ensure that the measurement of the thickness of the folded sheet is accurate. So you should normally, this question mostly every year comes. So you can say the thickness should be measured at different places and find the average thickness to reduce the random error. Or you can say that you will get 2 marks. Or you can say check for zero error to eliminate. Whenever you say zero error, eliminate, right? The word eliminate should be there. Or if you say random error, that means to reduce the random error. So you can say like this: measure the thickness of the sheet at many different places and find the average. That will reduce the random error. Or you can say check for zero error of the micrometer screw gauge to eliminate the systematic error. Anyway, those are normal questions. Even IGC, even year 12, that is unit 3, you had the same questions, right? Part B of the same question, 4 different photographs are given for micrometer screw gauge positions. In all those photographs, the zero point 0.5 division on the main scale is not visible. Only part of it visible. So we should not take the 0.5 millimeter. So if you read, you know, all of you would have done practical by using micrometer screw gauge. So the reading of they ask you to write the readings of the given 4 photographs. So the readings of the given photographs for the micrometer screw gauge. Okay, so these are the readings. You can get it from the photographs for the total thickness, that is for the 32 layers. Okay, calculate the mean thickness and the corresponding uncertainty. So mean thickness, you know how to find it. So that is first part, B part, second part. Mean thickness. So add all these things: 0.47 plus 0.49 plus 0.47 plus 0.49 0.48 divided by 4, that will be 0.48. I'm discussing that paper, right? Uncertainty, I already showed that for repeated measurements, uncertainty is equal to half into maximum. Among them, the maximum is 0.49 minus minimum 0.47. So that will be 0.01 millimeter, plus or minus you can say, right? Next part, the student weighed the folded sheet and recorded the mass 3.62. So the mass is given. Now see part, they are giving the mass 3.62 grams plus or minus 0.01 gram. So the answer is 0.01 gram. Calculate the value for density. So density, I need to find it. So the density equal mass over volume. So the total thickness, what I found here, this is for the 32 layers. I need to divide it by 32. They ask me to find the density in kilogram per meter cube. Careful. So it's a square sheet. The lengths are given already. 30.0. This also 30.0. So those are in centimeters. I need to convert them into meters, multiply, I'll get the area. Area into thickness give the volume. So simple or IGCSE calculations finding the volume. So I can find the density is equal to mass over volume. So mass, I need to convert this to kilograms. So 3.62, 10 to the power minus 3 kilogram divided by volume. So length 30 centimeter means 0.3 times 0.30, that is a meter, into the thickness. So I got the area. Thickness means this must be converted to meter, then divide by 32 to find the thickness of one sheet, because this is for the 32 sheets. So 0.48, 10 to the power minus 3 to convert millimeter to meter, divide by 32. So the answer you will get, density will be, normally we give it in 3SF, 2680 kilogram per meter cube. That's the answer for part C. Part C1, first part C. Okay, second part. It is suggested that the metal is aluminium, which has a density of 2710 kilogram per meter cube. Deduce whether metal could be aluminum. Okay, this is the final conclusion. So that means this is the thing I told, that the conclusion part, the purpose of this discussion is this one mainly. How to decide? You are given a sheet of some metal and you found the density through your experiment. You got, this is the density, this is the density, you got it. But the density of the aluminium, you have a standard catalog or somewhere, you found the density of aluminium is 2710. So you are going to decide whether my metal sheet, what I used in the laboratory, could it be an aluminium? So you can't say the aluminium density is given on the exam paper 2710. This is 2680. They are not the same. So how can we decide whether my sheet is aluminium or not? For that, I need to do some method. So what's the method? There are different methods we can use for that. Okay, the first method. Okay, the first method, I should find the uncertainty in the measurement of density in my experiment. I should find the uncertainty in the measurement of density in my experiment. Then I can find the range of my density value. Then you should check whether the given value, aluminium 2710 kilogram per meter cube, the given value, is it falling within my experimental range? If it falls within my experimental range, then I can say the material what I used is aluminium, right? Because the meaning is, I told the meaning of uncertainty. So if I say something I am measuring, the measured quantity X is equal to, say for example, 5.6 plus or minus 0.2. That means the range is 5.4 to 5.8. So what's the meaning of it? According to the given instruments, I am unable to give a precise value, but only thing I can say, my experimental value is somewhere between 5.4 to 5.8. But I can't give a specific value because my experimental instruments have uncertainties. So in this method, I'm going to find the range of the density of my measurement. So that means I can say my density is somewhere from here to there. Within that range, if the density of the aluminum falls, I can say, yes, the metal sheet what I used is aluminum. So that's the thing, first method I'm going to do now. So that's the first method. That is method 4, C part, second part. Okay, so I need to find, density is equal to mass over volume. I need to find the uncertainty in density. So their measurements are mass and volume. They are divided. So I can't find the uncertainty directly. I need to find the percentage uncertainty. Then I should find the uncertainty. So percentage uncertainty in density equal percentage uncertainty in mass plus percentage uncertainty in volume. I know volume is equal to length into width into thickness. Length into width into thickness, but length and width are same in this question because it's a square. Both sides have same length, 30 centimeter, 30 centimeter, right? Okay, so percentage uncertainty in density equal to percentage uncertainty in mass plus percentage uncertainty in volume. I taught that today when I started X over Y, right? Format. Okay, percentage uncertainty in mass. How do you find the percentage uncertainty in mass? We know the uncertainty in mass. The mass is given, uncertainty is 0.01 gram already given. So 0.01 divided by the mass is 3.62 into 100% plus percentage uncertainty in volume. So when the quantities are multiplied, I told that Z is equal to X into Y. So percentage uncertainty in Z equal percentage uncertainty in X plus percentage uncertainty in Y. So Z equal XY into K. Okay, whatever the number, how many different quantities, whatever the number of quantities we multiply, they will be added. Percentage uncertainty in Z is equal to percentage uncertainty in X plus percentage uncertainty in Y plus percentage uncertainty in K, right? So that method I should use here. So percentage uncertainty in V means V is given by length into width into thickness. So percentage uncertainty in length plus percentage uncertainty in width plus percentage uncertainty in thickness. Okay. So percentage uncertainty, again I'm writing without solving, 0.01 over 3.62 into 100 plus, so percentage uncertainty in L. So length is measured 30 centimeter plus or minus, already given in the first sheet, 30 plus or minus 0.1 centimeter. So that will be 0.1 over 30 into 100. Width also the same, 0.1 over 30 into 100 plus percentage uncertainty in thickness. Okay, thickness already we found it. We found the uncertainty in thickness 0.01 by using repeated measurements. So that is 0.01 that I discussed it already. The second part, B part, I already discussed 0.01 divided by 0.48 into 100. Okay, solve it. The percentage uncertainty, you will get it finally. So the percentage uncertainty will be finally 3.0. If you solve this one first and add it, you will get 3.1. Don't worry about it. We'll solve together. So you'll get 3.0 percentage. Right. So uncertainty in density. Value of density, you already found it. Value of density, we found it as 2680 into 3.0 over 100. So that's going to be plus or minus yeah, so the uncertainty will be plus or minus 80.4 gram kilogram per meter cube. Okay, so the range of density equal 2680 plus or minus 80.4. So that will be, we can get it 2600 from 2600 kilogram per meter cube to 2780 kilogram per meter cube. But the given value as the density of aluminium is given as 2710 kilogram per meter cube. Okay, so this value is falling within this range. You can see that the density of the aluminium is this much. The experimental value of the density, what I did in the laboratory, is 2600 to 2780. So that means I can say, according to the given instruments, I am unable to find the actual specific value of the density, but it is somewhere between this value to this value. The density of the aluminum is falling within this range. So my metal sheet could be aluminium. So that's a conclusion you should say. Finally, you should say, since the density of the aluminium is falling within the range of my experimental value, it could be aluminium. That's a conclusion. Okay, for the same question, same part, that is this question, the last part, that is taking decision whether it could be aluminum or not. So method 2, what I'm going to find, earlier I found the uncertainty of the density, then I found the range, and I checked whether the density of the aluminium is falling within that range. Okay, rather than finding the percentage uncertainty, I can find the range or the maximum minimum value by using the method what I already taught, by using this method. So I can say density equal mass over value. I'll find the maximum mass. Rho max equal to M max over V minimum, right? So maximum mass, what it be? The mass is given already in the question. Mass is given as 3.62 plus or minus 0.1 gram, 0.01 gram. Okay, I need to find the maximum mass. So in kilograms, so 3.62 plus, I should make the numerator maximum, 3.62 plus 0.01 into 10 to the power minus 3 kilogram. I converted to kilogram. V minimum. So that means minimum V means I should take all the minimum values for length, width and thickness. So length and width are given as same, that is 30 centimeter plus or minus 0.1 centimeter given in the question paper. The length and width are same, 30 centimeter plus or minus 1 centimeter. The thickness we found it from the photographs. The thickness we found, the mean thickness we got 0.48 millimeter for 32 layers, and the uncertainty we found it 0.01 millimeter. So one thickness means I should divide this by 32. Okay, so I can find the rho max. Then by using M max, I wrote it minimum volume. So all these quantities should be minimum length. That means length is 30 centimeter. Minimum is 30 minus 0.1 centimeter. So 30 minus 0.1. I am not writing that way. I'll write directly. So 30 minus 0.1 will be 29.9 millimeter. So I should convert 29.9 millimeter into meter divided by 100. So I can write 29.9 divided by 100 times the width, again 29.9 divided by 100 into thickness. This must be divided by this minus this. So 0.48 minus 0.01, that is 0.47. That is 0.47. 0.47 divided by 32, because 32 layers are there. That is in millimeter. Convert to meter, 10 to the power minus 3. So meter cube. I hope you understood that one. So I'm finding the minimum length, that is 30 minus 0.1, that is 29.9, divided by 100 to convert to meter. Same way for the width also. 0.47 millimeter, because 0.48 minus 0.01 is the minimum thickness. So I need the minimum thickness. Divide by 32 to get the thickness of one layer into 10 to the power minus 3 to convert to meter. Solve it. You will get the rho max. The maximum density 2760 kilogram per meter cube. Same way what will be the rho minimum. That I will write quickly. That is M minimum over V max. M minimum over V max. So M minimum, that is 33.62 minus 0.01 into 10 to the power minus 3 kilogram divided by V maximum, that is 30 plus 0.1. So that is 30.1 divided by 100 times 30.1 divided by 100 times, same way 0.48 plus 0.01, 0.49 millimeter divided by 32 to get one sheet into 10 to the power minus 3. So here you will get 2600. Okay, so you can see the minimum value of density is 2600, maximum value is 2700. So I can say the density of my experiment is from 2600 kilogram per meter cube to 2760 kilogram per meter cube. The density of the aluminium is given as 2710 kilogram per meter cube. That is falling within the range of my experimental value. So in this method also, you get the final answer the same. I can say since the density of aluminium is falling within the range of my experimental value, the given metal or the metal what I used in the laboratory could be an aluminium. Okay, so method 3, the third method for the same question, method 3, I should find the percentage uncertainty density as I did for the first method. I should find the percentage uncertainty. So density equal mass over volume, percentage uncertainty in density. I found it in my first method, so I am not doing it again. I found the percentage uncertainty in density in my first method for this question. I found the percentage uncertainty so the percentage uncertainty is, I found it as 3%, 3.0%. So I found it in my first method, 3. So you have to do again. If you are doing the third method, actually you should find it as I mentioned in my first method. Find the percentage uncertainty intensity. Then find the percentage difference between your experimental value and you found a value. You got a value for density. Without uncertainty, you got a value, is it? So you found a value for density. So find the percentage difference between your experimental value and the value given by the examiner as the density of aluminium. We'll find the percentage difference between those two values. So percentage difference equal difference over the given value, we'll take it as actual value. So percentage difference, you can find it like this. The density of the aluminium is given 2710. Our experimental value, we found it 2680 over 2710 into 100%. So you will get 1.1 percentage. Percentage uncertainty is 3. Percentage difference is 1. In any experiment, if we want to accept a value as acceptable value, then percentage difference must be less than percent. I don't need to go into detail why should it be like that. But if the experiment is correct, no mistake, but there are uncertainties due to the instrument you use, then percentage difference cannot be greater than percentage uncertainty, or otherwise I can say if the experiment is acceptable without any mistake, without any error, but there will be percentage uncertainty due to the instrument we use, then percentage difference should be less than percentage uncertainty. So here the percentage difference is 1.1, that is less than percentage uncertainty 3.0. So I can say final conclusion, since the percentage difference less than percentage uncertainty, the given material could be aluminium. I am finding the percentage difference between my experimental value and the aluminium. So the percentage difference becoming smaller than the percentage uncertainty in my experiment where I found the density. So I can say since the percentage difference less than percentage uncertainty, the given material could be aluminium. So this method also giving the same final conclusion. Okay, now I'll discuss this question, May 2019, WPH06, first question, Unit 6 paper. Right, so there they give a simple pendulum. They are giving the equation T equal 2 pi square root of L over G. The first few parts are nothing. Actually, they are asking a student displace the pendulum bob by a small distance to set the pendulum oscillating. The student measured the time for 10 complete oscillations. State the reason for using small displacement. You know the angle should be smaller, is it? The angle of oscillation should be smaller. That's the reason he should let it oscillate through smaller displacement. Then second part, the student used a pin as a timing marker. Explain how placing the pin at the center of oscillation would lead to more accurate value for 10t. So you can say if you keep it the pin at the center, the advantage, always the pendulum will pass that point. If you keep the pendulum or the pin at extreme position, you know, due to damping, sometimes it will not reach that point always. Second, you can say at the equilibrium position, if you keep the pin, the advantage, it will pass that point quickly. So those are the normal questions. So purpose of this question is the error calculation. Okay, so they are giving the time. Student is measuring time for 10 oscillations. So repeated measurements are given for 10t. He is measuring the total time for 10 oscillations. So those readings are given for 10 oscillations, repeated measurements. Okay, these are the values given for 10 oscillations. So the B part, first part, we need to complete the table, means we need to find the mean time for 10 oscillation. Find the mean time for 10t, the mean time for 10t, add them and divide by 5, you will get it, 10.24 seconds. Then they ask you to find the mean time, the mean t divided by this 10, 1.024 seconds. So that is nothing. Okay, so second part, B part, calculate the percentage uncertainty. So percentage uncertainty means careful. The given data for 10t, this is for 10t, this is for 10t, repeated measurements for 10t, not for 1t. But they ask you to find the percentage uncertainty for t. Careful, I already told that. You find the percentage uncertainty for 10t, half, max, minus, mean, right? That will be the percentage uncertainty for t also. I told that. You are going to find the mean value, divide by 10, but when you are dividing or multiplying, the percentage uncertainty will never change. So I can say they ask you to find the percentage uncertainty in t. I will find the percentage uncertainty in 10t is equal to half maximum. So the maximum among them is 10.32 minus 10.15 divided by the mean 10t, that is 10.24 into 100%. So that will be 0.83%. That is for percentage uncertainty for 10t. So therefore percentage uncertainty for t, that also the same. I told that by dividing by 10, the percentage uncertainty will not change. Okay, so C part, they are giving, a student says that there are two different pendulums. One pendulum is double the other one. So they are telling the period of double pendulum as TD Shorter pendulum is Ts, the double of it is Td, the period of time. Now, student says that Td squared over Ts squared should be 2. That is the theoretical truth. We can show that. So, they asked you to justify the prediction by the student. Td squared over Ts squared should be 2. Okay, so here Td squared means double the length of it. So, you can divide it Td squared over Ts squared is equal to divided, you will get 2. So that is the theoretical value. When the length become double, the square of the larger one, double the length over time period for smaller one will be 2. Theoretically, we can show that. Okay, so that is nothing. So this is the theoretical value. So the question is, experimentally student is doing. So we found already the time period for smaller pendulum. We already found it. We found the average time 1.024. We found the percentage uncertainty. Now when the length is doubled, they are giving the time period 1.461 plus or minus 0.011 second. So they are asking determine whether the results support this prediction. This is the theoretical prediction. So when we do it experimentally, will it support this theoretical model? We'll see that. Okay, so this is the value given for double the length of the pendulum time period. For shorter pendulum, that is half of it initially when we do, we found it already in the part B. We know that Ts is equal to 1.024 plus or minus. We know it in percentage uncertainty, that is 0.83 percentage in terms of percentage uncertainty. Okay, so we need to find the uncertainty there. Right, so we need to conclude whether these values tally with experimental value. These experimental values, will it give the theoretical value, that is Td squared over Ts squared is 2? Will it be given through the experimental values? Okay, we'll find here also Td squared over Ts squared will be equal to 1.461 squared over 1.024 squared. That will be, you will get 2.036. Okay, so I need to find the percentage uncertainty in this value. Percentage uncertainty in Td squared over Ts squared equal, this is index, so 2 times percentage uncertainty in Td plus 2 times, this is denominator, so there also we should add them when we are dividing it, 2 times percentage uncertainty in Ts. You know, I can write, if you want one step, I would have written it, but I didn't write. Percentage uncertainty Td squared plus percentage uncertainty Ts squared. I can write here if you want. Td squared, percentage uncertainty Td squared plus percentage uncertainty Ts squared. Percentage uncertainty Td squared is 2 times percentage uncertainty Td. Percentage uncertainty Ts squared is 2 times percentage uncertainty Ts. Now solve it. So that will be 2 times 0.011 divided by 1.461 into 100 plus 2 times, I already found the percentage uncertainty 0.83. So that will be 3.2 percentage. So find the uncertainty. That is, we know that 2.036 into 3.2 over 100, that will be 0.065. Okay, so then I should find the range of Td squared over Tx squared. So range of that is 2.036 plus or minus 0.065. That will be from 1.971 to 2.101. So that means the theoretical value, I proved it in the previous part, Td squared over Ts squared should be 2. I already proved that by using 2 pi root of L over G, I derived it. So that is the theoretical value. Practically, I can say through my experimental results, I can say TD squared over TS squared, I am getting somewhere between 1.971 to 2.101. But the theoretical value, which is 2, is falling within this range. So my experimental results is supporting the prediction because the theoretical value 2 is falling within the range of my experimental value. Therefore, it is supporting the prediction. Okay, so these are the type of questions again comes in the past paper, but only the equations what they are giving might be different. Okay, so here also you can find the second method, find the percentage difference. You know the experimental value of this one 2.036. Find the percentage difference between this and 2. 2 is the theoretical value. Find the percentage difference. You will get percentage difference will be smaller than percentage uncertainty 3.2. That is another method. Method 2, I can say, find the percentage difference between your experimental value and the theoretical value, which is 2. Okay, difference over actual value, which is 2 into 100. Then compare with the percentage uncertainty, you will see the percentage difference is less than percentage uncertainty. That way also you can say, since the percentage difference less than percentage uncertainty, I already told that if the experimental value is acceptable, percentage difference between your experimental value and the actual value must be smaller than the percentage uncertainty. You will get smaller value, try it. Then you can conclude in this method also. Either one, you don't need to do the both. So there also you can say percentage difference is less than percentage uncertainty, you will get it. It supports the theory. Okay, I hope you understood. So in my next lesson, I will discuss a few recent past papers in Unit 6.